Hey guys, Professor Dustin here, and I'm going to talk about energy and harmonic motion in this video. So we've already talked about forces in harmonic motion. We talked about the horizontal system of the block attached to a spring on a frictionless surface. As the block moves back and forth, the spring force pushes on the block or pulls on the block to make it go in this harmonic motion, bouncing back and forth to its most compressed state to its most elongated state. So now we want to talk about what's going on with the energy in this system. So I have here written some energy bar graphs. So these are just pictorial representations of what the energy is doing as it gets traded between kinetic energy of the block and the potential energy of the spring. So recall that the potential energy of the spring is 1/2 k delta x squared. So that k is the spring constant, that delta x, that's just the amount the spring is compressed. So if there's no compression in the spring, this delta x is 0. And if it's at its maximum compression, this delta x is equal to A. So initially, as the block is going through equilibrium, there's no potential energy in the spring. All the energy is in the kinetic energy of the block. The total energy is just k plus u, so the total energy is equal to the kinetic energy of the block. This is supposed to be halfway in between the equilibrium point and the maximum compression point. There's some kinetic energy because the block is still moving, although a little slower, but there's some potential energy as well because the spring is now a little compressed. The sum of those two things is again equal to E, and notice that I've made the bars about the same size because energy should be conserved in this system. All these green bars had better be the same if we're going to have conservation of energy. So as the block reaches its most compressed state, it has no kinetic because it's being stopped. All the energy is in the potential energy of the spring. K plus U is again equal to E. As the block shoots back, again, it gets some kinetic energy, loses some potential, and we have E. And back here again, we have entirely kinetic energy, and here we have entirely potential energy, and this cycle continues to repeat. So just based on this nice picture, we have an image of how energy is being traded around in this system. We can also get something out of it. We can write an interesting relationship using this information. So let's start with this one. So I can write the total energy in the spring as just the kinetic energy. So right here, the total energy is going to be just equal to the kinetic energy, and of course that's just 1/2 mv squared. That's a true statement about this initial point, right? So let's pick another point. I'm going to pick the point of most compression. Now the total energy is still going to be k plus u, but now there's no kinetic energy, and there is some potential energy. There's the most potential energy, 1/2 k times the amplitude squared. Is the amplitude squared because the amplitude is the point of maximum distance from the equilibrium. That's this point A, and so that's where the most potential energy will be. But now we have two relationships that both represent the total amount of energy. So we can set those two things equal to each other. And that gets us 1/2 mv squared equal to 1/2 k a squared. So there might be some complicated things happening in the in-between points, right? There can be some other speed, some other 1/2 mv squared here, and some other compression, 1/2 k delta x squared here. But we know there's a relationship between the maximum values, between the amplitude and the speed of the block as it goes through the center. So this basic argument is going to help us understand the energy in the spring and other kinds of harmonic processes when we start actually doing problems. Okay, so thank you guys for watching. This has been Energy and Harmonic Motion. I hope it's been useful, and I will see you next time.